on, so this can feel like a roundtable discussion rather than sort of like shouting into the void. But if you want to say stuff in the chat, I will amplify. Well, you can discuss among yourselves, but then I will amplify into the conversation. Tian, were you going to do the introduction? Here.
Sure. Welcome everyone. Today's speaker is Ranjan Rohatgi from St. Mary's College, and he will be talking to us about graph labelings, new theorems, and open problems.
Well, thank you all for coming. And I just want to thank the organizers for asking me to talk today. I hope it's going to be fun for everyone. I want to amplify what BK said about people commenting and participating and making this more of like a conversation. I'll probably ask you to do some math along the way too. So yeah, you should do that. And then you can, travel in the footsteps of my undergrads who solved some of these problems last year. So Yufei Zhang, you can see her name next to mine. She was the undergrad that I primarily worked with, and the two of us ended up publishing a nice paper in a hybrid journal, which requires some student authorship. And I think it was a great problem for like an advanced undergraduate. And it kind of started with, I was her professor for discrete math, her junior year, maybe, I'm not quite sure. Yeah, it was her junior year. And she really loved the subject, and I do combinatorics and graph theory, so I love the subject as well. And then she received a grant to do some undergraduate research over the summer, and that's kind of where all of this started. So I want to start at the very beginning with going back all the way to chromatic numbers. So I've drawn a graph down here. It's got, 4 vertices and 5 edges. We can call this guy G. And if we just want to, if we want to label the vertices so that they're all different, not all different, so that no vertex is adjacent to a vertex of the same color. So we can do that. Let's see how we can do that. Maybe we label that one blue, and that one can also be blue because they're not touching. But then the other two, neither of them can be blue because they're touching the first two. So we can make this one red, and we can make this last one green. And now no vertex is adjacent to a vertex of the same color. And so this is a vertex labeling, is what I'm going to be calling it. And the chromatic number, which we haven't proven is 3, but you can prove that 3 is the fewest number of colors that you can do this with. And yeah, so rather than calling this a coloring, I'm going to call it a vertex labeling. And more important than for this talk than the colors of the vertices are the numbers. So the 1 and the 2 and the 3. We can also do something similar with the edges, where the rule is that if the edges meet at a vertex, they also have to be different, get different labels. So now that the colors don't matter so much, I'll just use one color when we go and label these edges. So maybe we can label this edge 1 and this edge 1 because they don't meet anywhere, but they meet all the other ones. So then I think we can do 2 over here and 2 over here because those edges don't touch, and then 3 for that edge. And so we're going to call this guy an edge labeling. And we write chi prime sub G. Again, we didn't prove that it's 3. We proved that it's, at most 3. But you can prove with a little bit of work that you can't use any fewer than 3 colors here. And this is written chi prime of G. And we're going to call these edge labelings. All right, so these are kind of things that you might learn in first semester of graph theory at some point. But let's make it more complicated. So now we have the same graph G, and we're gonna do what's called a total labeling on this guy. And so the rules here are a little different. So we're gonna label both the vertices and the edges, and both of those have to be labeled like normal. So if edges meet then they can't share the same label, and if vertices are adjacent, they can't get the same label as well. But also, an edge and the two vertices that it's touching have to be different colors as well. So let's take a look and see what we can do here. So I don't know, we can give that vertex the number 1 and that one. And now we also have to label edges. And I think the edge in the middle can get a 1, 2. I actually didn't try this example before we started, which maybe is not wise. But we'll see what happens. So those can be 1s. We can give maybe this vertex a 2. Now we can't give the other vertex a 2 because they're adjacent, but I think one of the opposite edges, maybe this one, we can also give a 2. And at this point, I think we have to go to 3s here. So yeah, this should work out. 3 here and 3 here. And then these can both be 4s. I think that looks right. So now no vertex is adjacent to another vertex with the same label. No edge shares a vertex with another edge that has the same label. And an edge and a vertex that any of its end vertices, they don't share the same label either. And so these guys, this is called a total labeling, and it's written double prime, chi double prime of G, in this case is 4. So, all right, let's make it maybe a little bit more complicated, another type of labeling. And these have been studied, these are called graceful labelings, and these have been studied at least for maybe 50 or 60 years. And the rules here are a little different. So we have to label the vertices with the integers from 0 through m distinctly. So all the vertices have to get distinct labels. And here m is the number of edges. So I guess in this case, m equals 5. And then we label the edges with the absolute difference of the vertices, the end vertices of that edge. So we don't have any choice. In the total labeling, we had a choice for vertices and edges. Here, we don't have a choice. We have to take the absolute difference of the end vertices. And then the goal is that all edge labels are distinct. All right, so let's try to do this. So let's suppose oh yeah, and it's 0 through m. So I can use a 0, and m here is 5. So 0, 1, 2, 3, 4, and 5. So let's suppose we try something like this. If we label the vertices 0, 1, 3, and 5, then let's see what happens with the edges. So we gotta just subtract. So 1 minus 0 is 1, 5 minus 1 is 4, 3 minus 0 is 3, and then these are both 2, 3 minus 1 and 5 minus 3. This is a problem, right? So one of the conditions, condition 3, is that all the edge labels are distinct, but these are both 2, and that's bad. And in fact, these differences are actually going to be, they have to be 1, 2, 3, 4, and 5, because we're labeling with 0 through m. So since they're all distinct, they're going to be 1, 2, 3, 4, and 5. So I think we can do this. I think this graph is graceful but we have to be a little bit more sneaky about it. Since we have to get a 5 for one of the edges, the 0 and the 5 have to be adjacent. And then I think we're okay. So if we do it this way and then look at the edge labels that we get by subtraction, 5, 4, 3, 2, 1, and so that works. Notice with graceful labelings, unlike with other labelings, we're not trying to necessarily minimize something. We're told explicitly what the labels have to be. The labels on the vertices have to be from 0 through m, and the labels on the edges have to be distinct. So those will end up being from 1 through m. So the issue about graceful labeling is more of like a yes/no question. Does a graph admit a graceful labeling or not? And then there are more questions from that, but graceful labelings are a yes/no question for a particular graph, whereas vertex labelings, edge labelings, total labelings, you can do all of those, but you're trying to minimize the highest vertex, the highest label that you use. All right, so this was some background for what we ended up doing. And so how did we get to this? And this is where kind of great opportunities for undergrad research come into play here. So we have our vertex labelings that my student learned about in class, as well as our edge labelings. And then those combine kind of with an additional condition to get us total labelings. And then separately, there are these graceful labelings. And so what Yufei and I did was really combine these two ideas here. And we call this, we call these, and I'll define them in a minute, total difference labelings. And I'm not sure whether labelings has 1 or 2 L's. So like, I think I'm just going back and forth at this point. So that was our idea, and it worked out quite well. But it also wasn't our first attempt at finding a problem that was interesting. If you combine things that are in the wrong way, that problem can be fiendishly hard. If you combine them in the wrong way, the problem could be trivial. But basically, my idea was let's just combine types of labelings. And a great place to get information about what's out there is Joe Gallion has this like compendium of results on graph labelings of all sorts of types, and he just keeps updating it constantly. I think at this point there's over 2,000 references in there, and so you can kind of look at and see what's been done and what hasn't been done and just find something and go for it. So yeah, so that was the idea. So let's define these things. Okay, so here are the rules for what we're calling total difference labelings. So first, just like normal, we label the vertices with positive integers. And again, right, so adjacent vertices have to get different numbers. We label, just like in graceful labelings, the edges with the absolute difference of the end vertices. But unlike in Graceful, where the edge labels were then specified to be 1, 2, 3, 4 up through M, our only goal is that the labels now, the vertex labels combined with these absolute difference edge labels, form a total labeling of the graph in the sense that we just talked about. All right, so let's take a look at this graph G, and let's do an example here. So, okay. So we're labeling the vertices with positive integers. Let's just take a stab at this. 1, 3, 4, and 7. And if I pick those properly, this should work here. So now we're going to subtract. So 2, 1, 3, 6, and 4. And then now we should check that these green numbers and these red numbers combined form a total labeling of this thing. So adjacent vertices we know have the same labels, but we see a couple of 1s, we see a couple of 4s. That's okay here. They just need to form a total labeling. They don't need to do what graceful graphs have, which all of the edge labels are different at this point. So as long as those 4s aren't adjacent in any way, and similarly with those 1s, we're good. And so I think this example works. And so we've shown, we called this guy chi sub TD for total difference. And we've shown that this is less than or equal to 7 at this point. If we're sneaky about it, I think we can get it smaller. But this takes a little bit more thought. 1, 5, 6, and 2 should also work. Let's see here. 4, 3, 4, 5, and 1. Yeah, so that works as well. And so we've minimized, or not minimized, we haven't proven that we've minimized it yet, but we've gotten it smaller than 7. So actually chi TD of G is less than or equal to 6. And so this was the kind of thing that Yufei spent her summer doing. So let's play around with this for a little bit. And here's where I'm going to ask you guys to jump in. All right, let's see if we can figure out what chi TD of Pn is. So remember, we label the vertices, the edges get the absolute difference of the adjacent vertices, and then that has to form a total labeling. So anyone want to jump in with an idea or a thought here?
Seems like it should be less than n.
Yeah, sure, right? It can be I would believe that it should be less than n, because we can just go for it.
So it's symmetric, and I want to like take a set of labels that goes up and then comes back down.
Okay, well let's start. Let's just throw a 1 at the beginning, because why not? What could go on that next vertex right there?
3.
Great. So we'll get a 2 up here. What can go on that next vertex?
2.
Yeah, so we could put a 2 here. And then that makes this guy a 1. And now we got to get a little creative here. Yeah, so this one's going to jump up to 5. So the reason this jumps up to 5 here is if we put a 3 right here, then this edge is a 1. If we had put a 4 here, then this edge is a 2, but this vertex is already a 2. And similarly, we can't put a 1 here, because then we have a 1 right in this spot and a 1 right in this spot. So yeah, we'd have to jump up to 5. So we can do that, but actually there's a way to do it without jumping up to 5. So if we don't put a 2 there, we throw a 4 in here, then we can just repeat this pattern as long as we want. And that can go on forever. So being greedy isn't always the right way to do things, but it can help us. So we can just keep following this pattern as far as we want. And so as long as you have at least 4 vertices, chi TD should be 4. I think if you have fewer, if you have 3 vertices, right? BK had said that we could go 1, 3, 2 on those vertices. That would totally work. But yeah, as long as n is greater than or equal to 4, we can do it in 4. All right, great. So that was our first theorem. Let's get another one out of this. Cycles. All right, so I'm going to claim that one of the results for cycles is we already did.
Multiples of 3, was it, from the previous
Yeah,
one?
exactly. Right. So this pattern back here repeated every 3, and so if the number of vertices is a multiple of 3, then it's 4. So right, so 1, 3, 4, 1, 3, 4. Okay, what if we have this guy over here this one is C7. All right, how are we going to do C7? Anyone want to float an idea out there?
Can you put a 5 between the 1 and a 4?
Oh, sure. That might do it. 1, 3, 4. 1, 3, 4. We should be able to do it with 5. The problem with this construction, though, is that we get these ones right here.
Yeah.
Maybe if we just swap those, that would be sufficient. Maybe, maybe not.
Could we put the 5 between the 3 and the 4?
Yeah, let's try it. So if we put the 5 between the 3 and the 4, so the problem here now is that 1, 3, 5 right here. But maybe if we put it between the 1 and the 3, it might work.
Isn't that still 2 and 2 next to each other?
If we put the 5 between the 1 and the 3, there should be a 4 and a 2 next to each other,
sorry.
right? No, you're good. I also did not remember how to, I did not look this one up before we started. I figured we could figure it out on the fly. And this looks like it should work. 2, 1, 3, 4, 2, 1, 3. So yeah, that'll work, right? And we can extend this because we can just throw in copies of 1, 3, 4, like say in between here, as long as we're, this is 7. So 1 mod 3. And something similar should work for 2 mod 3. You might have to throw in 2 5s rather than just 1, but similarly, we can, let's just say that we proved it because it's just a construction here otherwise. All right, let's do one more of these together. So interestingly, complete bipartite graphs, we had a conjecture for it, but we didn't end up trying to prove that result. But complete bipartite graphs got a little complicated kind of quickly. But this result about stars, where one side of your complete bipartite graph just has one vertex, was super useful, especially when we applied it to more complicated types of graphs here. So, so let's try to label these stars. Just based on intuition, what labels kind of make sense for the lone vertex?
One.
Yeah, so 1 could totally work there. 1 would make a lot of sense to go right here. And then how can we do the rest of these?
Edges 2, 3, 4, 5.
Yeah, so the only issue is we can't use a 2, because if we use a 2, then we'll have the edge connecting them, like, right, we'll get something like this,
Sure.
which we don't want. But other than the 2, we're good to go. So we can just do 3, 4, 5, and 6 if we wanted.
I was talking about the edges, but yes.
Oh, sorry. Yes, you are absolutely right. Yeah, my bad. You're perfect.
No.
So yeah, so this would work. In this case, there's actually a better way to do this. We can actually just do it in 5. And for that, let's just draw this guy over here. If we label this one 5, then we avoid the issue of like a multiple of 2 or half. And so then we can just go 1, 2, 3, 4. So sometimes we can actually, it's just equal to the total number of vertices. I drew this example where M was 5 over here because that won't work. So the issue with this example over here on the right is if you put a 1 right here, you still have to skip 2 over here. So you'll go 1, 3, 4, 5, 6, 7. But you can't get smaller than 7 because if you put a 6 over here, then you got to skip 3 on the other side as well. So either way, for, if M is odd, you can't quite do it with just the number of vertices. So the result here is that it's M plus 1, which is the number of vertices, if M is even, and it's M plus 2 if M is odd. All right, so a couple of observations. So we basically, I think we noticed, especially in this last example, that we can't have something like this, because then the edge and the end vertex are the same, get the same label, and that's bad. And then what was the issue that we kept running into with the cycle? That was basically that we would have two edges that were incident that had the same label. So that could happen kind of in two ways, right? If we had something like x plus y, x plus 2y. So if we had like an arithmetic progression here, then both of these are y's, and that's bad. And then the other issue, the other way that this something similar could happen is, right, so it's not quite an arithmetic progression, but it's two vertices that are distance exactly 2 apart that are the same. So that can't be the case either. And so, yeah, so we called these guys doubles and these guys triples. And then basically the idea was we just need to avoid doubles and triples. So now we can actually go back to our example that we started with. So we proved that chi TD of this graph G here was less than or equal to 6. Now we can actually prove, if we want, we can prove that it actually is equal to 6. So yeah, we can try it. So how does this proof work? So let's start by proving that it's got to be at least 4. So I think one of the key observation here is basically this thing about triples. The point about triples, at least the second definition of triples down here, is that if you're distance 2 away from another vertex, you have to be different. You can't get the same label. And in here, all vertices are distance at most 2 apart. And so all of them have to get different labels. So that's like the first observation. So all the vertices get different labels, but so we can try to prove this by contradiction. So if chi TD of G is equal to 4, then must use 1, 2, 3, and 4 each exactly once. So that we get from looking at triples. But then once we have that, then we can look at doubles, right? The vertex with the label 2 can't be adjacent to the vertex with the label 1 or the one with the label 4. And that's just the problem. Right, so every vertex up here in G has degree at least 2. And so it's got to be adjacent to the 1 or the 4, and then it won't work. All right, so now we know it's either 5 or 6. And I think we can now prove that it's 6. Basically, at least when we started, we did graphs of like simple graphs with few edges and few vertices pretty early on. And it was basically just case analysis. And that's all really that's going on here. I think there are 5 cases that we got to talk about. We can go through them kind of quickly. But the idea is, all right, so if it's 5, then what happens? Well, either the 5 is at a degree 2 vertex or it's at a degree 3 vertex, which is these 3 cases. If it's at a degree 2 vertex, we know a 4 has to appear somewhere. And the reason a 4 has to appear somewhere is if it doesn't, then we get a 1, 2, and a 3 in a triangle. And that's impossible because you'll have 2 edges that both get the number 1. So then your 4's got to appear, and then you just got to look at basically at doubles and see what happens, right? So up here, neither of these vertices can be a 2. And actually, neither of them can be a 3 either, because then you get a 3, 4, 5 triple or a 3, 4, 5 triple. So both of them have to be 1s, and that's obviously not allowed. And you can go through this one the same way. So down here, right, neither of these can be 2s. So you have to have a 1 and a 3. But if you have a 1 and a 3, then you'll get a 1, 3, 5 triple at some point. So you'll get a 1, 3, 5 triple, and that's bad. And then we can do the same thing by looking at if the 5 is on a degree 3 vertex. It's a little, there's 3 cases now because you don't necessarily have to have a 4 in here. So this case up here, right? So if there's no 4, so we have a 5 at a degree 3 vertex, there's no 4. So we have to have a 1, 2, 3. And the 3 and the 1 can't be in the same triangle because you'll get a 1, 3, 5 sequence. So the 2's got to be here, but then you get a 1, 2, 3. And then you can do the last 2 cases if you want. Assuming there's a 4, look at your doubles and see what happens. So that was the kind of thing that we did a lot of early on. And we were able to do, Yufei was able to do quite a bit. So she determined chi-TD for wheels and some variations of wheels. One of the I think the most involved proof was determining chi-TD for all caterpillars. You can get a bound for it using what we did for stars. And then after you get a bound, then explicitly classifying it was quite involved. Long enough that we actually didn't put the actual classification proof in the paper because it like doubled the length of the paper. But it was a lot of good work that she did there. And then she also got bounds for lobsters and trees. Those bounds were fairly naive based on what, I mean, they were based on what we had done for stars, but they weren't very much, they didn't go very much beyond that. So definitely open problems is, yeah, you can consider other graph classes for sure. So that's another thing you can do, right? So the first one was to combine different types of graph labelings in ways that hadn't been done before. You can go and take this one and run with it. The key theorem that helped her do a lot of that helped her prove the caterpillar result was essentially that the observation that we made that a total difference labeling basically meant no doubles or triples, she proved it. Those things are equivalent. So she reduced this from a question about labeling vertices and edges to just one about vertices. And so when you think about it like that, the other direction that you can take these types of problems in is you can define other forbidden configurations of vertex labels and then try to minimize the maximum label used. Whether you want to define the edges via the difference or some other combination of edge labels, that's totally up to you. But there's a lot of problems that are still out there. I just want to throw, before we just open this up, I just wanted to throw a few ideas out there. So harmonious labelings basically they look at the sum modulo something or other. So that's how you get the edge label. You look at the vertex labels and take their sum modulo the number of edges, I believe. So you can combine that with total labelings. You can also combine things with rainbow labelings where everything is distinct. Everything has a distinct label. In general, some problems are harder than difference problems, but you can also define labelings however you want. You can always, even with difference labelings, you could always label the edges first and then figure out what the vertex label should be from there. Like that's induced from the edge. It's a little more complicated because there might be more than 2 numbers, but that's doable as well. So yeah, I mean, that's what I got for you. Combine some different labelings, go further with our ideas, or look at these like forbidden configurations and see what you can get. There's a lot out there for sure. So thanks.
I think the main question in the chat right now is, what is a lobster?
Oh, cool. That's a great question. So a caterpillar basically is a path. So first of all, these are all kinds of trees. A caterpillar is a central path, and then all other vertices are distance at most 1 from that central path. And then a lobster is a caterpillar with more appendages, but only 1 layer more. So we can add, and again, it's still a kind of tree. So central path, every other vertex is at most distance 2 from the central path. So here's an example of a lobster. Yeah, someone said, like, if I don't remember which mathematician said this. If you take a lobster, or I don't know, you have a caterpillar and then it like cocoons into a lobster or something biologically that made no sense but was funny.
Benjamin, did you want to explain what you were thinking about that you call balloons that turned out to be dragons?
When I looked at the Graceful labeling Wiki page a long time ago, the picture there is like a cycle with like a single, I don't know, just a bunch of edges coming. And so I was like, okay, I'll just call them balloons and everyone will know what I mean. And when I started to Google aggressively, people call them dragons, people call them canoe paddles, people call them tadpoles. It seems like the nomenclature is not standardized.
Something like this?
Yeah, and then that last piece that you drew could be much longer.
Ah, okay.
And then the question that I had was, is it true that all such objects admit graceful labelings? And I found out through people having called them different things that the answer existed and was yes, but no one had ever combined those two pieces of literature in the past. Yeah, lollipop also very reasonable. Canoe paddle, I don't know.
Stop sign? Well, that only works for an octagon or something.
People were curious about your app. They found the chalkboard nature of it very soothing.
Oh yeah, this is Explain Everything, which I think my school pays for a license for it. But yeah, like they have some built-in templates, and I like the chalkboard one. But then when you export it to PDF, it's a really big file if you use the chalkboard.
And Michelle had some questions back a long time ago about example of a graph that doesn't admit a graceful labeling.
Oh man, maybe Ben's the right person to ask for that.
Or Dan asked about multiple graceful labelings.
Yeah, that's totally an area of research where I know work exists, but I'm not sure about any of the results there.
You know where Yufei is now?
Yeah, she is a PhD student at Notre Dame.
Cool.
So right across the street from us. So if she ever wants to come back and do some more of this stuff, maybe she can.
Do you have a link to the paper you could put in the chat? So
oh yeah, sure. Absolutely. Let me find it. Yeah, there's a version. There's a version on the archive.
I'll vamp for you all. So part of this was about how to generate new questions to work on with research students. So has anybody been inspired for a new question they think they might work with a student on? Either to share out loud or in the chat?
I think if we have the paper, I mean, I could show that paper to students and let them ask their own questions. I mean, I think it's really good to have a paper like that co-written by a student recently, and it's very accessible, and it would be inspiring for the students to see that. So I think this is really wonderful, and I'm looking forward to maybe not this semester, but within a couple of years, maybe using that. So that looks really great. Thank you.
Yeah, and one thing I didn't even mention, when Yufei has given talks about this, she presented this whole thing as like a game, not as like a 2-player game, though there might be a version there. But she was like, here's just like a puzzle, and let's see how many of these puzzles we can solve. And I think that got a lot of her classmates kind of like interested in playing around with it.
I will admit I was kind of thinking like this should be the next Sudoku or whatever.
That's what I was thinking. I was thinking it would be cool if there were like a PDF file that had just some of the, basic kind of graphs and sort of walked you through like the setup for what the rules are. Because I could see, my 9-year-old like taking all these things on like a Sudoku puzzle and trying to figure out like, where to put the 6.
Yeah, I definitely have my outreach hat on right now.
Now I think this could be adapted to be a great math circle activity or something like that too.
Yeah.
Somebody needs to do that. One of these smart people needs to do it. No.
Do you know if Yufe is still studying graph theory?
She's in her first year. I think she does want to study something in combinatorics or graph theory. So hopefully she does. Yeah, that would be great.
If anyone knows how to turn this into a math circle type activity, I'm interested.
This might be related to that question, but it's kind of like, can you generate good, is there sort of like a backwards algorithm of like generating a good graph that you definitely know has one and what it is somewhat algorithmically? Because you can imagine quickly creating a lot of puzzles for people to solve if there is a nice sort of backwards algorithm.
Yeah, so so every graph will have this chi-TD number, but I don't think, if you just look at complete graphs, already the pattern for chi-TD, it's known, it's on the OEIS because it's equivalent to, say, no arithmetic progressions of size 3 and no doubles, almost. So the sequence of values for like complete graphs is known, but not like, I don't think there's a closed form for it. And so I'm hesitant to say like, oh yeah, I can just come up with a bunch of these that would be easy in like a whole class of these that would be easy.
Cool. Any other questions? Well, I'll do a little advertising before we wrap up. Oh, I am not allowed to share my screen.
Oh.
So I'll just say our talk next week is by Belim Senajini. Belim, are you here? Okay, I saw your name earlier.
I'm here.
Great. Would you like to give us a very brief preview?
Sure. First of all, thank you, Ranjan. Yeah, it's cool seeing you again. Some years ago, he came to a computer algebra program on GAP at U of A. So it was exciting to see him doing this. So next week, I'm doing a version of the talk I gave at the JMM. So kind of an examination on diversity and equity in mathematics programs and trying to analyze those diversity and equity and inclusion initiatives from the point of view of how solar colonialism perpetuates resource extraction. And it's going to be a version of JMM because lots has happened since JMM. And so I'm trying to incorporate some of the more current conversations into that talk next week.
Excellent. Looking forward to it. All right. Would people like to unmute to thank Ranjan?
Thank you.
I started making all kind of weird doodles on his artwork.
Same.
Don't tell them. I'll get in trouble.
Tell your friends. This will be up on YouTube soon, and I don't know, it seems like a great one to share with students, and you should all join us next week. Yay!